All right, well, it is 12 o'clock, so we're going to go ahead and get started. Welcome everyone to NC-ASA's second webinar, and thank you so much for attending. I'm Emily Griffith. I'm the president of the North Carolina chapter of the American Statistical Association. The NC chapter and our industry interest group are excited to bring you this webinar today. We will have 2 more webinars in this series this year, a professional webinar in the early fall and another machine learning webinar later in the fall. Please keep an eye out for those announcements. The North Carolina chapter is one of the largest ASA chapters, and we have a really active community with a lot of events. Please take a look at our latest newsletter, our website, or our social media accounts to find something else to attend. Again, thank you for attending this webinar. If you have any questions during the webinar, please type them in the group chat. Funda will read through those during the questions period at the end. Funda Gunesh is a principal machine learning developer at SAS. She does research and implements new data mining and machine learning approaches for SAS, visual data mining, and machine learning. Her experience and research interests include combining well-established statistical methods with algorithm-based models, assessment and validation of machine learning models, efficient feature engineering techniques, regularization and machine learning algorithms, stacked ensemble models, and Bayesian statistical modeling. Through her work at SAS, she's given expository talks on new machine learning and data science techniques, both internally and externally at major machine learning conferences. She's written technical papers and blog posts and created short videos. In addition to machine learning, she's also an experienced statistician in clinical trials, survival analysis, mixed models, and longitudinal data analysis. Funda holds a PhD degree in statistics from NC State University. So without any further ado, I'd like to turn this over to Funda.
Thank you, Emily, and other organizers, Sujit and Elizabeth, for organizing this event and giving me an opportunity to talk about machine learning at NC-ASA webinar series. Hi all, thank you for joining me at this webinar. We have a pretty ambitious topic to discuss in 1 hour today, Introduction to Machine Learning Techniques. Machine learning is a very broad area, and as you can guess, we will be able to talk about just tip of the iceberg today. My hope is to give you a basic idea of machine learning. After the webinar, I'm hoping you will all have answers to questions such as, how is machine learning different from traditional data analysis and statistics? What does training a machine learning model means? What are popular machine learning algorithms? And what is the biggest problem when you train machine learning models? What techniques and tools you can use to avoid this problem? Then we will briefly talk about difficulties in explaining black box models, and I will introduce you some simple methods. In the end, I would like to run a 5-minute SAS visual data mining and machine learning software demo, showing you the software I work on for my day-to-day job at SAS. And if I have time, I also would like to talk about machine learning as not just algorithms. Data exploration, pre-processing, such as cleaning, feature engineering play a very big role in producing good predictive models. If I don't have time to do that, please don't get too disappointed. This might be a good topic on its own to discuss at another webinar. So what is machine learning? Machine learning focuses on enabling algorithms to learn from data without being explicitly programmed. Instead of giving a stochastic model, you feed the data to a generic algorithm and it builds logic based on the data given. Even though AI and machine learning was first introduced in 1950s, over the past few years, it's exploded. Much of this has to do with the wide availability of GPUs that make parallel processing ever faster, cheaper, and more powerful. It also has to do with infinite storage of data and that whole big data movement. Now data comes in all forms, images, text, transactions, mapping data, you name it. With this explosion, we all suddenly found out that AI and machine learning is already a part of our everyday lives. For example, every time I receive a voicemail on my phone, I can see the written transcript right away. Another example is internet search engines. Even though we have search engines for a long time, it's amazing how quickly we can reach the information by just typing a few keywords. My last example is product recommendations we get from sites like Amazon based on our online shopping history. In all those examples, machine learning algorithms are running behind. I can easily add more applications that use machine learning behind, such as autonomous cars, face recognition for safety applications, and Google DeepMind's success with AlphaGo in beating world champion in Go game, which is considered much more difficult for computers to win than other games such as chess. It looks like AI will continue to shape our future more powerfully than any other innovation in this century. And I feel like anyone who doesn't understand this will soon find themselves feeling like left behind, waking up in a world of technology that feels more and more like magic. So I'm very glad to see a record number of registrants for this webinar who wants to understand and contribute to this field. So a good way to start learning about machine learning is to think about how data are generated, because our goal is learning from data. You can think data are generated by a black box in which a vector of input variables come in one side. Oops, sorry. I'm trying to use the laser pointer. Vector of input variables come in one side and the output comes from other side. So there are two goals in analyzing data. Inside this black box, nature functions to associate the input variables to the response variable. So we can think that the data is generated by this black box. And the goals are, there are two goals, and these are prediction and interpretability. In prediction, the goal is to be able to predict what the responses are going to be for future inputs. And the other goal, extracting information, is about learning how nature is associating the response variables to the input variables. And there are two different approaches towards these goals. Leo Breiman, who was one of the pioneers of machine learning and a well-known statistician from Cal Poly, called these two approaches as two cultures. I took this image from his popular article, Statistical Modeling, Two Cultures, that was published in 2001. He defines statistics culture is more focuses on extracting information to understand the relationship, how nature is associating input variables to the response. Whereas the other culture, predictive modeling, or machine learning culture, focuses on predicting the response. Machine learning culture approaches the problem with the understanding that how nature interacts inputs with the response is a very complex dynamics, and lets algorithms learn this relationship and tell us what the predictions will be. These algorithms are very smart learning the relationship, but very complex in nature to tell what the association between the variable, between the inputs and the response. So in statistics, parametric modeling culture, we start analysis with assuming a stochastic model for inside the black box. This culture makes assumptions about the data, which can greatly simplify the learning process, but it can also limit what can be learned from data. Stochastic modeling involves two steps: select the form of the function and learn the coefficients of the function from the training data. Some examples of stochastic or statistical parametric modeling are linear regression and logistic regression. In statistics, we validate models by using tests such as goodness of fit tests, which often favors more simple models compared to complex models. For validation, we need to check the assumptions of the model. For example, if model assumes normal noise, you need to check if the residuals are normally distributed. So simpler models can help us understand the association better. So in statistics, parameter interpretability of the model is important. In the machine learning culture, on the other hand, considers inside of the black box is unknown. And the approach is letting an algorithm finding a function that operates on input variables to predict the response Y. Algorithms learn from data by not constraining it to a specific form or structure of the model. They do not make strong assumptions about the form of the mapping data. Some examples are support vector machines, neural networks, decision trees, ensemble of trees. By not making assumptions, algorithms are free to learn any functional form from the training data. This often requires more computation power because you need to go through data many times, and each pass-through data, the algorithm can learn something different that can be added to the existing complexity. And model validation is based on predictive accuracy of the trained model. We train models by only using one part of the data and use other part of the data to test how good that model is in prediction. So machine learning models are good at predictions, but as I mentioned before, they are often very complex. And as humans, we don't have cognitive abilities to understand how input variables are related to the response, whereas statistical models are more interpretable. So for many years, these cultures kind of ignored each other. There were not much collaboration. Machine learning research conducted in computer science departments, whereas statistics research was conducted in statistics departments. But I feel like things are changing now. Statisticians now recognize computer science making novel contributions, while the computer science now also recognize the generality and necessity of statistical theory and the methodology. So although initial goals of those two cultures were different, it's now more converging. In statistics, there's a lot of research going on making those stochastic models more predictive, have more predictive power. In machine learning culture, there's a lot of research going on for explaining these models, especially for their use in regulatory industries, because they need explaining, people need understanding of those models. So I will briefly talk about some of the interpretability techniques of black box models towards the end of this webinar. In machine learning, there are different types of learning. Some most popular ones are supervised, unsupervised, and reinforcement learning. In supervised learning, we draw inferences from the training data set that includes input variables and labeled responses. So computers studies data with labels until it can apply labels on its own. This is the most commonly used machine learning type and also the focus of today's tutorial. For example, in a fraud detection problem, input data includes the set of input variables such as amount, time, or location of the transaction. For each transaction, a labeled response include if the transaction was fraud or not. A supervised machine learning algorithm uses this labeled data to learn the patterns common in fraudulent transactions. The more the data, the better the algorithm gets learning about those patterns. A well-trained model can predict if an ongoing transaction is fraudulent or not in a real time with high accuracy. Another example of supervised learning is image classification. Data includes images and label for each image if it is a car, cat, or dog. By studying these labels of each image, algorithm learns patterns present in track pictures that are absent from others and start to build its own cognition. The more cats the computer sees, the better it gets in recognizing cats. Therefore, it's called supervised learning. So other type of learning is unsupervised learning, where the data does not include a labeled response. The most common unsupervised learning technique is cluster analysis. For example, marketing firms kindly use hundreds of behavior and demographic indicators to segment customers into targeted offer groups. Unsupervised learning techniques quite useful in providing humans with insight into the meaning of data and often provide new useful inputs that you can use in your supervised machine learning model. For example, this newly created customer segmentation variable that you get from clustering can be used as a new feature in your supervised learning stage. The other machine learning technique, excuse me, is reinforcement learning. In reinforcement learning, the basic idea is taking actions and learning from those actions, just like a puppy dog or a child starts out exploring without really understanding. They move from exploring to exploring. So every single page at Amazon.com is implementing this loop of exploring and exploiting, showing you stuff, trying to get you click, and whether you click or not matters. This is how the system learns more and more about you by moving from exploration to exploitation. So reinforcement learning is commonly used now in gaming industry. For example, in a computer game, a chicken can learn to safely cross the road without any software engineering cheating that's implemented by a smart algorithm. So I want to clarify one thing. Up to now, I use AI and machine learning interchangeably, but actually, in general, AI is a broader concept of machines being able to carry out tasks in a way that we would consider smart. I consider reinforcement learning more of an AI than just machine learning. It is very likely that we will see more advancement in the area of reinforcement learning, but this topic is beyond the scope of today's seminar. So before we start to talk about popular supervised machine learning algorithms and how they work, let me show you some applications. One, we already talked about this. One well-known application is fraud detection. Fraud can involve cell phones, insurance claims, tax returns, credit card transactions. Again, the data might look like something, and we call this a tabular data, and it includes a label, which is the response that tells if each transaction was fraud or not. Fraud modeling is usually more powerful if you have like strong signals in the input data set. For example, in addition to amount, time, and location of transactions, if you create new features such as time since last transaction, difference between transaction amounts, difference between location of transactions, you can significantly increase the predictive power of your model. Often, original data does not directly include these nice features, and you need to go ahead and construct or extract this relevant information from other data sources, and this is called feature engineering. My next example is an image classification problem. In this case, input data includes 70,000 images. Each image is a handwritten digit, and we also have a label for each image. By studying these images and labels, algorithm learns how number 9 is different from number 8 and so on. And the goal is to classify each handwritten digit as numbers 0 to 9. So to analyze this kind of data, we need to convert image to numeric form. Each image is 18 by 18 pixels. You can think each pixel in an image as a feature in your input data that takes a value between 0 to 255 based on how dark it is. Converting image to numeric data is part of pre-processing for image data. So other pre-processing can include cropping the center of an image, scaling, creating a mean image, and normalizing each image by subtracting the mean image from each image. So in image data analysis, data augmentation is also commonly used to increase the sample size. The more the sample size, the better the algorithm can recognize different patterns, such as they do augmentations by rotating the picture. Once the pre-processing is done, you need to feed data to a supervised machine learning algorithm. For analyzing image data, we often use neural network-based algorithms such as convolutional neural networks. Computer compares the patterns of numbers against already known objects. Then for each new image, it assigns a confidence score, a probability if it belongs to the group 0 or 1 or 9. The class level with the highest confidence score is usually the predicted one for that image. This is another image classification problem. Here, the goal is to classify objects into 10 classes. Classes include common objects such as airplanes, automobiles, birds, cats, and so on. The data set is split in a standard way where 50,000 images are used for training a model and remaining 10,000 for evaluating the model's performance. And state-of-the-art results are achieved by using convolutional neural networks, which is better than human performance. Another application is in computer-generated faces. As recently as a few years ago, most AI-generated headshots look like the poorly done police sketches. But things have changed. The ones you see here are generated by NVIDIA's generative adversarial networks called StyleGAN by using a deep learning technique called style transfer. These faces look so real. Having said that, there are a lot of ethical concerns about this application. For example, using this technology, you can perfectly overlay faces on different bodies, make people whoever you want, or forego someone's fingerprint or other biometric data. There are a lot of discussions going on around this. Another use case of supervised machine learning algorithm is for recommender systems. Here you see a list of recommended books. When I search for my favorite statistics book, the elements of statistical learning. Another example is recommending movies to users based on tens of millions of past ratings. Inherently, the recommendation models are trained based on similarity metrics, such as similarity between the users, similarity between the items. The data is often very large because there can be millions of users and items. Moreover, it is very sparsely observed because only a very small fraction of the historical ratings will be available. So the algorithm that is for recommendation systems need to be able to work well with this kind of sparse data. We talked a lot about tabular, not a lot, but one example of tabular, and I show you several examples of image data. Data can also come in the form of text and audio. Analyzing this type of data is collected under natural language processing. There are so many applications in this area. Some popular applications include spam filtering, classifying email text as spam or not, sentiment analysis, finding out what customers think of your brand by analyzing raw text clues about positive or negative sentiment. And it returns a sentiment score between 0 to 1 for each document, where 1 is the most positive. Another application is key phrase extraction, automatically extracting the key phrase that quickly identify the main points of a text. For example, for the input text, such as something like this, the food was delicious and there were wonderful stuff. The algorithm returns the main talking points, food and wonderful stuff. Another application is in speech recognition, transcribing a speech, for example, creating text captions for a movie or a show, language detection among spoken languages, detect what language the text is written or spoken. Okay, next I would like to cover algorithms. If you're a data scientist or want to be a data scientist, you don't need to fully understand how algorithms are working, but you need to have some basic understanding, such as what are the strengths and weaknesses of those algorithms, what type of target they support, which algorithms can embrace parallel computing the better so you can run it faster, how do they deal with missing data, if they work well for sparse data, how complex the models are, how interpretable the models they produce are some of them more interpretable than others, and the list goes on. So let's start with regression. Regression is not truly a machine learning algorithm. This is a modeling technique that we steal from statistics. However, it can be used in machine learning. in regression analysis, the relationship between the input variables and the response is defined by the stochastic model that you see here, which is a linear function of input variables. And here we have an interval target, a numeric target. To fit a regression model, we need to find the regression weights, which are this beta 0, beta 1, beta 2, which is found by minimizing this objective function that you see here. Once you find a best model weight, you can use this model to score a new data set for prediction. In regression models, it's very important to eliminate collinearity and redundancy of the input variables as much as possible to minimize overfitting. If you're also planning to use your regression model to extract information about the effect of input variables, you need to pay special attention to collinearity between the variables, because as you have more collinearity between the input variable x1 and x2, they will have larger standard errors. Logistic regression is another technique borrowed by machine learning from the field of statistics. It is a go-to method for binary classification problems. So we have a binary target. Different from linear regression, the prediction for the output is transformed using a nonlinear function called logistic function. The logistic function looks like this big S that you see here that transform any value into the range of 0 and 1. This is useful because we can apply a rule to the output of the logistic function to snap values 0 and 1 to predict a class value. Like in linear regression, logistic regression does work better when you remove features that are unrelated or correlated to each other, highly correlated to each other. So in predictive modeling, regression modeling is a fast and simple modeling technique. We often use it as a baseline model. Here are some things to think about when you're using regression. Do you have outliers in the data? Outliers can be very highly influential in resulting fitted lines. Suppose you have an outline here. If you don't have enough sample size, it can shift your fitted regression line. How about missing values? Regression cannot handle missing values. If there is a missing value for a variable in your tabular data for one variable, you end up losing the whole row of information unless you do some kind of imputation. And imputation, we always need to be very careful when we do imputation because the missingness itself can be very informative. So even you do missing data imputation, I highly recommend creating an indicator for so that your algorithm can learn about this missingness pattern. Regression modeling is also very sensitive to collinearity between the variables and also the redundancy. So it requires you to perform a good feature selection first. And one way to minimize collinearity and overfitting is to apply regularization, such as lasso or ridge regression, that allows you to apply those regularization and minimize overfitting. I will talk more about regularization in the coming slides. However, in predictive modeling, the biggest problem with regression is that it cannot capture nonlinearity well. The only way to account for nonlinearity is to explicitly add interaction terms, quadratic or spline terms to the model. Deciding which terms to add gets time-consuming and tricky as the number of variables increases. Because regression cannot capture nonlinearity well, and what can be learned through a model is limited through that defined stochastic function. So the prediction accuracy may not be as good as black box algorithms. Decision trees, on the other hand, which is a machine learning algorithm, can learn this nonlinear relationship naturally. Decision trees learn in a hierarchical fashion by repeatedly splitting your data set based on a variable into separate branches that maximize some kind of information criteria. This branching structure allows trees to naturally learn the nonlinear relationships. They make new branches until they reach leaves. They represent the predictions themselves. For example, here we have a simple tree for a housing data set where the goal is to predict value of a house based on a set of input variables that includes housing type, such as single family or townhouse or lot size. This tree learned that for single family houses, larger lots are more expensive. However, this is not true for smaller houses like apartment, condo, and townhouses. This can be related to locations such as probably smaller apartments and townhouses might mostly located in urban areas. In a linear model, to take into an account of this type of nonlinearity, you need to explicitly add an interaction term for lot size and house type to your model. On the other hand, decision tree can capture this naturally. So there are some advantages of using decision trees. I just listed one of them. It can naturally learn nonlinear relationship. Missing values are very easy to incorporate because it's based on the splitting and the majority of the votes. So it's robust to outliers. It's more interpretable than other black box models, but of course less interpretable than a regression model. It also, the interpretability depends on the depth of the decision tree, how big that tree is. And also it provides an out-of-the-box variable importance table. So even though by using this table, we cannot tell if a variable had a positive or a negative effect to the response, like in a regression model, this table gives us a list of variables that are ordered in importance based on their role constructing the tree. And so that kind of gives us some information. One weakness of decision tree is that individual trees are prone to overfitting because they can keep branching until they memorize the whole training set. That's why we usually, when we do decision trees, we keep them growing and then we prune back so they can generalize well to new data. So I already talked a lot about overfitting. Let's just, let me try to explain what I mean by overfitting. Overfitting is the biggest problem in training machine learning models. It refers to a model that models the training data too well. It happens when a model learns the detail and noise in the training data to the extent that it negatively impacts the predictive performance of that model on a new data. For example, here, on the right and the left, we have the same data but different models. The plot on the left shows an overfitting model where the noise or random fluctuations in the data is picked up and learned as concepts by the model. The problem is that these concepts do not apply to a new data and can negatively impact the model's ability to generalize. Ideally, you want to select a model that looks more like this curve on the right. It does not capture all the points as well as the curve on the left, but it is more generalizable to a new data set. There are techniques that can help us monitor overfitting of the models at each iteration of the algorithm. And the two commonly used techniques to monitor overfitting is to monitor prediction error by using a separate validation set or cross-validation. So to understand overfitting better, it is important to understand variance and bias trade-off of models. As models get more complex, you see like in this x-axis, this is the complexity, their variance shown in blue curve increases. And on the other hand, as complexity increases, their bias decreases. So it's hard to get a model that has both low bias and low variance. And the total error of the model is bias plus variance, so this green curve. When we train model, we would like it to have a small prediction error, total error. So we would like to have a model somewhere here where this shows the kind of optimal balance. Not too complicated complexity, but also not too simple too. This is the model that can generalize well to a new data set and can give us a good prediction. So how to find this model? Some techniques to find to a model somewhere here is to use regularization and ensemble learning, model ensembling, and hyperparameter tuning. Next, I will talk about each of those techniques. So arguably, the best way to deal with overfitting problem is to use some form of regularization for the model weights when you train a model. Here, I'm showing this for a linear model, but regularization can be applied to any kind of machine learning models. So remember the minimization problem that we had for a regression problem. The goal was to find a regression base by minimizing this loss function. In regularization, we minimize this loss function based on subject to some constraints on the regression weights. For L1 regularization, which is lasso, this penalty is on the sum of the absolute value of the regression coefficients. And if you're using a ridge regression, you want to minimize this error as long as your regression coefficient, sum of the square of the regression coefficients, is less than this positive number t. So what is this number t and how we can find this? This is a hyperparameter of a model. And I can only solve this model minimization problem using an optimization technique if I know what the value of t is. And even I have a lot of experience, had a lot of experience analyzing data, I cannot generate a good value of t that would work for all different types of data. So it requires some tuning, trying different values, fitting the model, and seeing how good results you are getting and changing its values. One advantage of using regularization is the lasso regularization is that it can remove some coefficients entirely from the model. So it does a simultaneous variable selection while it's giving you a regression model and regression methods. A good rule of thumb is to always use regularization. As I say, this is not specific to regression models, especially if you have so many parameters, so many input variables in your model. And you can use regularization with other machine learning models, such as decision trees, neural nets, and so on. So another way of that helps us to, another way to minimize overfitting is to use ensemble learning. The idea in ensemble learning is to train multiple models. These are often called weak learners, or I like to call them regular learners, that are trained to solve the same problem and then combine these models to get better predictive model. The main hypothesis in ensemble modeling is that when weak models are correctly combined, we can obtain more accurate and more robust models. So building powerful ensemble models actually has many parallels with building successful human teams in business, science, politics, and sports. Each team member makes a significant contribution, and individual weaknesses and biases are offset by strengths of other members. So each regular learner tend to be a complex and overfitting, and hence each will have higher variance because they're complex, such as individual decision tree model that I showed you earlier. But when we combine and build an average tree, we get a more robust model that can generalize well to a new data set, somewhere close to the optimal model that we have seen in the variance and bias trade-off graph. For doing that, bagging is a commonly used technique in ensemble modeling. In bagging, the idea is to generate multiple versions of the training data by sampling with replacement from the training data. Then we train a model for each sample and combine these results. So I would like to explain a little bit what I mean by combining different models. Suppose you have a tabular data, you have a prediction that comes from each model for a single row. You simply get the prediction from multiple models and average them. This is the simplest kind of ensemble learning, but it can be done in more structured way that I will discuss in model stacking. So going back to bagging, what we do is we simply do bootstrap sampling, and we create multiple versions of the training data. And by doing that, we kind of try to generate what the input data might look like in the future, because it can be very different from the data that we have in hand. So we are adding some diversity into our training set, which would give us a more smoother curve, like you had seen in the overfitting plot, instead of a model that explain all the noise and in the data. So this idea is very similar, such as estimating a quantity from a data sample, such as mean. You take lots of samples from your data and calculate the mean, then average all of your mean values to give you a better estimate of the true mean. The idea in ensembling modeling is very similar. So the other kind of ensemble learning is based on boosting. Boosting combines the same kind of regular learners, such as decision trees, that are learned sequentially in an adaptive way. So in bagging, we have different training set, and we independently train models on those training sets. Whereas in boosting, we train a model, and in the next, we build the next model based on the first model by correcting some errors of the first model made. And stacking is another technique that combines heterogeneous regular learners. So it doesn't need to be all decision trees. It can be a neural network model, a gradient boosting model, and a forest model. So I will talk each of those in more detail in the coming slides. So ensemble learning enables us to take advantage of the flexibility of decision trees while preventing them from overfitting to the training data. Instead of building one decision tree model, multiple trees are trained on random subsets of the data that's obtained by bagging. And in addition to using different versions of training data, forest model also introduces further randomness by using random sets of variables to choose each splitting variable when they are building those decision trees. So two sets of randomness is introduced here. It's and then once all the models are trained independently, combine the predictions. This could be, as I said, if it's an interval target, just a simple average, or if it is a classification problem, it would be a majority vote. I really like random forest modeling because it doesn't have very many complicated hyperparameters to tune, and it just performs well right out of the box. Gradient boosting is another ensemble method that uses decision trees. Instead of training decision trees independently, decision tree models are built sequentially. This is done by building a model from training data, then creating a second model that attempts to correct the errors that comes from the first model. For example, if an instant is not predicted well in the previous model, the next model gives more weight to that instance to get it right. Similar to forest, bagging is used to get different, also uses different versions of the training data here that are obtained by bagging. After all trees are built, we ensemble them. Because so much attention is put on correcting mistakes by the algorithm, it's important to have a understand your outliers in the data. So in model stacking, enables you to combine different kinds of model. In forest and gradient boosting, it was all combining decision tree models, but in model stacking, you can combine a factorization machine model, a neural network model, and a support vector machine model. Suppose I generated a decision tree model, my teammate generated a support vector machine model. They are all good models. To increase the predictive accuracy, we might choose to combine the predictions that comes from each model. A simple method would be giving the same weight to each model. Or if we believe one of the model is much better than other, we can choose to give a higher weight to that model and give a lower weight to the model that's not performing that well. And we can still, doing that, get an ensemble model which would perform better than each of those three models. So instead of guessing what each model weight they will take, and in building an ensemble model, I can do this more intelligently by training a second level algorithm. So I have predictions coming from a decision tree model, predictions coming from a support vector machine model or a decision tree model. I can use these as inputs and use my response to estimate the weights where each of those models will take. And this is called model stacking. It's commonly used in data science competitions. I have a paper with Russell Finger, one of my colleagues from here from SAS, and he is in jump division and one of my mentors. We had written a good paper about this. You can take a look at that. I also have a blog post about model stacking. Model stacking is especially popular in data science competitions, in which a sponsor posts the training data that includes the labels and test data that doesn't include labels, and issues this big global challenge to produce best predictions for a specified performance criterion. Winning teams almost always use ensemble models instead of a single fine-tuned model that is trained by one machine learning algorithm. Often, individual teams develop their own ensemble models in the early stages of the competition and then join forces in the later stages. One such popular site is Kaggle. And if you don't know Kaggle, I encourage you to explore numerous spinning solutions that are posted in the discussion forums to get a flavor of the state of the art. Another popular data science competition is KDD Cup. Here you see the winning solution for the 2015 competition, where a three-stage stack modeling approach is used. At stage, to add further diversity, instead of using a fixed set of features, they generated 7 different feature sets and trained 64 models. At stage 1, this is this stage, 64 single models are fit by using various machine learning models, including neural network, forest, gradient boosting, and such. And these are single models. And this is the this is the stage where ensemble modeling is performed. Predictions from these 64 models are used as inputs, and they're combined in various ways to generate those 15 models here. At stage, and then at stage 2, the predictions that comes from these 15 models are used, and they're combined with a gradient boosting and a logistic regression model. And in stage 2, only these 2 are used as input and combined by using a logistic regression model, as you see here. To build powerful predictive models like this, diversity is the initial plays the key role. So we see that they are training using different algorithms. Probably they are using different hyperparameter settings. They're using different feature sets. And another way to introduce diversity, like we talked before, is using different training sets. So you don't need to always work with the same set, same single training set you have. You can create different versions, fit models, and ensemble them too. One way of doing adding diversity is to just randomly sampling features. If you have like thousands of features, and create models for each feature sets and then combine them. As I said, the goal here is to add as much diversity as possible so we don't produce an overfitting model, a model that can generalize well to a new data set. So the next algorithm that I would like to discuss is neural nets. Looks like we are running out of time, so I will try to go a little quickly at this part. In neural networks, input values, or in other words, underlying data get passed through this network of hidden layers until they eventually converge to the output layer. The output layers are prediction. The hidden layers of a neural network perform modifications to the data to eventually understand what the relationship between the input and the output layer. Suppose you have three inputs, x1, x2, x3. They each take different weights to perform those neurons. And on top of this, a nonlinear activation function f is applied to introduce nonlinearity. And this is important because the most real world data is nonlinear, and we want neurons to learn nonlinear representations. Doing this over a few layers, a neural network is be able to understand and manipulate the data into something meaningful. To figure out what these small weights, like the weights here that you see by those arrows, we typically use an algorithm called backpropagation. Andrew Ng, who has a popular Coursera course on machine learning, uses this term of lazy hikers to explain how most machine learning algorithms end up working. A hiker doesn't actually know where she's going. She just feels around to find a path that might take her down to a mountain. Our algorithm is the same. It's feeling around to figure out how to make the most accurate predictions. In 1980s, most neural networks were single layer due to the cost of computation and availability of data. Nowadays, we can afford to have more hidden layers in our neural network, hence we can have deep learning. And here you see a simplest form of neural network, which is called feed-forward network, and the information moves in only one direction. From input nodes to the through hidden layers to the output node. There are no cycles or loops in the network. Different types of deep learning methods are available, such as convolutional neural networks, recurrent neural nets, long short-term memory, where each have different use cases. Deep learning is especially effective in analyzing image, text, or sound data. We typically don't use deep learning for analyzing tabular data like you're seeing for the fraud detection. It is a special kind of a deep neural network. It's a special kind of neural network. The deep in the name comes from the number of layers in the network. The traditional neural nets includes 1 or 2 layers, but deep neural nets can include as many as 150 layers. One of the most popular deep learning techniques is convolutional neural networks. They have, I'm not going to go into detail like fully connected layers, pooling, dropout, flattening. A lot of the things are like special techniques to neural networks to account for overfitting. For example, in pooling, you reduce the amount of parameters to minimize overfitting, or dropout is similar. You try to decrease the number of parameters because you don't want to learn too much from your training data. Convolutional neural networks includes convolutional layers at the beginning Instead of feeding the entire image as an array of numbers, the image is broken up into a number of tiles. The machine then tries to predict where each tile is. Finally, the computer tries to predict what is in the picture based on the prediction of all tiles. So this allows computer to parallelize the operations and detect the object regardless of where it is located in the image. So all those applications require a lot of data, while adding more data does not change the performance of traditional machine learning. For example, a regression model, you can add more and more data, you will see your model is not changing because you're restricting what model can be learned with the stochastic form. But they can make a big change for modern machine learning algorithms, especially for deep learning. Think about this, an autonomous car has to experience situations over and over again to master them, training to cope with every possible traffic and weather situations, and this requires so much data. So the predictive performance continuously increases for largely deep neural networks as you add more and more data. And large computing companies such as Google have been able to create powerful speech and image recognition applications by spending big giant collections of label training data. But getting vast amounts of label data for every domain can be very difficult considering the time and effort it takes to label these data. I recently joined a talk by Tesla, and one of the things their lead scientist was saying, they have a group of people, data scientists, and their only job is to label data, and the algorithms takes care of the rest. So in traditional machine learnings, the models are built from scratch. But there's this new technology or method called transfer learning, is the modern approach that enables utilizing the knowledge for one task to solve the other tasks. And the motivation for transfer learning goes beyond specific tasks and domains, and you can leverage this information by using pre-trained models. I'm not going to go into the details of this because I don't have much time, but at SAS and SAS Maya, Visual Data Mining and Machine Learning, we have this pre-trained models that can enable you to solve problems even you don't have a large label data. And as I say, those the domain does not necessarily need to be the same to be able to use transfer learning. So in general, neural networks, higher prediction accuracy, works well with large number of features such as image data. It's black box, it requires big data and requires tuning for large number of hyperparameters, and it often requires GPU power to be to analyze. So Emily, do I have 5 more minutes to go over model assessing?
I think the webinar is going to cut off in about 10 minutes.
Okay.
But we could schedule another webinar to talk about model assessing.
Yeah, maybe.
But we could do maybe like 1 or 2 minutes.
Yes, I think that will be a good idea because I have quite a bit slides. I would like to talk about each of those methods here and wanted to run a demo. So I think scheduling another webinar would be a really good solution. So
perfect. Okay, so we're seeing like people are commenting that would be great. So thank you. There is a question if you wanted to answer that really quickly. So the question, are you ready? Or
yes,
do you want
let me go to my last
real
slide.
Okay.
Sorry.
Yeah, I'll let you do that.
As I said, I had quite a bit, really good slides still remaining, and I'm more than happy to get together with you one more time to finish, including model interpretability and cross-validation and all those nice techniques. So interpretability methods. So I think Cynthia Rutten will go over in more detail explaining black box, explaining models, but I had some good slides here too about model agnostic interpretability methods that can be applied to any machine learning models. And I want to quickly go over to my last slide. Okay. Okay. Yeah, I'm ready for the questions. Hello?
Okay, great. Yeah, sorry, I had muted myself. So the question is, in general, is the model used to combine the ensemble models a less complex model like gradient boosting or a random forest?
So it depends on the ensembling method you're using. If you're using stack ensembling, instead of like combining weak learners, which can be really complex, we are looking for really strong models. For example, you know, you might have a very good model with area under the curve 95. I can have another model with area under the curve 95 too, but those two models can be different, so that they will be good candidates to use in stacking. Whereas in boosting and bagging, they don't really necessarily need to be strong learners. So yeah, they can be each be overfitting and weak learners, but then when you ensemble them together, you get a better model because you decrease the variance of the models by including for some diversity among the models.
Great, thank you. All right, well, thank you everyone for attending, and thank you, Funda, for such an interesting and informative talk. I know that I learned a lot from listening to it. For everyone who's listening, the webinar is going to be posted on NCASA's YouTube channel, and the link to that will be available on our website. So if you want to share this talk with your colleagues, it will be up by Monday for you all to view and share. We will definitely get another one on the books because this was so great. And I hope that we will see all of you at another NCASA event soon. So thank you so much.
Thank you all for joining.